Hi, in this lecture, we present mechanisms used to provide both integrity and authenticity of data. Remember, the goals of cryptography are confidentiality, integrity, and authenticity. And so far, we've focused a lot on encryption which provides you with confidentiality. So here, we'll talk about hash functions and message authentication codes, otherwise known as MACs. And those mechanisms really are here for the other goal to ensure the other goals of cryptography, so integrity and authenticity. So first, let's talk about hash functions because they're going to be a building block for the MACs anyway. So the basic definition of a hash function we've seen in our first module is very simple. It's a function that takes inputs and produces outputs of fixed length. So really, you want the elements of the domain to be bit strings of arbitrary length, or at least length bounded by something extremely long. And the output is a tag that is of fixed length. So this is our symbol for a hash function throughout this lecture. Now, as such, there is nothing really complicated about a hash function. So the real question is what kind of security guarantee we require of the hash functions. Now, one interesting fact here is that it doesn't even require the key to evaluate. So it's at first glance is a little surprising, especially because we've emphasized a lot the role of symmetric key encryption schemes where to evaluate and decrypt the encryption and decryption, everybody needs the key. So here we have a function not requiring any secret. What kind of security guarantees could we possibly ask? So the first one is the pre-image resistance. So in a nutshell, it means that if I give you an image, so a tag, it must be hard for you to find an X such that h of X gives you this tag. Okay, and that's the first pre-image resistance. Now you can also define a sort of you can also define a second pre-image resistance by saying that you're given y as h of x prime. Okay, so you're also given a pre-image for the element that consists in the challenge. Okay, now the second pre-image resistance to find an x that is not equal to x prime, that equals y. Okay, so that's the first goal, is pre-image resistance. Another goal is collision resistance, and that means that it must be hard to find x and x prime that are different and somehow hash to the same tag. Okay, so that's collision resistance. So these are the security guarantees that we require of hash functions, and as you can tell, none of them mention keys. Okay, this is all about I give you this public hash function, and your challenge is to find inputs with certain properties. Now, how could we possibly use a hash function in a way that it provides some kind of security guarantees, most likely in terms of integrity? So the integrity of downloaded data is an example of how to use hash functions in cryptography. So let's assume that Alice is downloading data from a website. Okay, we can have the website publish the tag of the data. So that could be a software, and then there could be, for example, a tag that is a hash of the software, a hash of the source code, or a hash of the binaries, and they publish it on their website. Now, for this to be secure, we have to assume that the website is really read-only, so nobody is able to tamper with the website. But then once she downloads it, she wants to figure out that she has the right version of the of the data. And so to do this, she hashes, okay, and she gets another tag, and then she compares with the tag that is being displayed, okay. And she hopes that the tags are going to be the same. If they're the same, then if the hash function is secure, then we're talking. Then we know that the data that was downloaded is exactly the data that was given by the software by the software company. Now, if the tags are different, then Alice knows that whatever she's getting is not the data that the website intended to send her. Now, password verification is a very famous example of where we can use hash functions. So in this case, we have Alice has a password that she sends to a server. Okay. Now the server does not check directly a password. Instead, they hash it and they get their tag, and then they compare the tag to what they have in their database. Okay. So this system prevents, I mean, it allows a service, the server here that Alice is trying to connect to, it allows them to not have on their database the passwords of all of their users. And that's really important because so if they had all the passwords of their users, it could create a situation where if they get hacked, then all the passwords of their users are being compromised. Instead, if they get hacked, people can only look at the tags, so only the hashes of the passwords. And it turns out that if the hash function is pre-image resistant, then it will be hard for people to retrieve the passwords, okay, or anything that hashes the same tag for that matter. So now there are mechanisms, of course, to make this even more secure using the so-called salting technique, but we're not going to get into this in this lecture. Another really popular application of hash functions is proof of work. So a proof of work, as its name says, is the proof that a certain amount of work was being done. Now, what do we mean exactly? Assume you have a hash function and input data. Then you hash it together with a number, and that number changes. So you take a number 1, 2, 3, and you increase. And you hope that the hash has a certain property. So you get as bit strings, and sometimes you have a certain number of initial zeros when you look at your bit string that is the tag of the data that is hashed together with a number. So every time you get a different number here with the same data, you get a different bit string, and sometimes those bit string have the property that there are many initial zeros. So if you ask for, say, a number k of initial zeros, then the probability at each given step that this happens is 1 over 2 to the k. So the expected number of hashes, it's an expectation only, not exactly the number that you'll have to produce. You can be lucky or you can be unlucky, but on average, you'll have to produce 2 to the k hashes in order to obtain a hash that has k initial zeros. Now, what does this mean? This means that you will produce on average about 2 to the k hashes in order to find the right number here, such that your data hashes to something that has k initial zeros. And that could be a lot of work if k is a large number. On the other hand, anybody who wants to verify your work only has one hash to produce, right? You just give them the number and the data and they can verify. Okay, so that's really interesting that you do a lot of work to find a certain value, but the verification of your work is almost instantaneous. Now, who uses proofs of work? Well, one very, very popular example of application of proof of work is blockchain technology. In blockchain, you have data, a lot of data that is chopped in blocks and is stored by multiple nodes that potentially do not know each other and do not trust each other. And so a user connects to one of the nodes and expects to see the same version of the data, so of the blocks of data, that they would see by connecting to any other node. So it's a decentralized storage of a system of data where nobody trusts each other. Now, the thing is, each of the nodes competes at every time step to add the next block of data. And how do they compete? So they take a block of data that they need to add. So for example, in the case of the Bitcoin blockchain, it's a block of transactions, okay, transactions of cryptocurrencies. But in general, blockchains can have a lot of information that is not necessarily a cryptocurrency transaction. So every node will, I mean, potentially every node will want to be the one adding the next block. And of course, they are incentivized, which means that there will be a reward for the one that will be adding the new block. But how do we decide? Well, we get them to perform a proof of work on, as input, the data that is the proof of work of the previous version of the blockchain and the new block, okay? So this proof of work here, the data, consists of both the previous proof of work and the next block. And then there is going to be, a winner in this competition, because this number 2 to the k hashes, of course, is an average value. Some people will finish sooner than others, and that's because when you have a different data here, then you'll have different values here, okay? And so whoever wins gets to be the one to add the next block, and then they propagate the results to all the other blocks. And then it's in the other block's best interest to verify first that the proof of work is valid, and then start working on their next proof of work, where the input now is going to be the new version of the blockchain. Now, there's nothing preventing a particular node from trying to add their own block, okay, once they finish their proof of work, and then to continue adding new blocks to a fake version of the blockchain, and hoping then that the clients that connect to them will believe their version of the blockchain. Now, the only reason not to do this is because all this work has to be done for every subsequent block, okay? Even if you add new blocks that are the valid blocks of the blockchain, you still need to do the proof of work, and it will be verified very easily. But the problem is you don't get the reward, right? Only the winning node will get the reward. And so it just becomes very, very expensive. And that's the primary reason why the blockchain is secure, is because it's very, very counterproductive to cheat. Now, let's talk about the design of hash functions. Typically, hash functions are defined as, a compression function, okay? At least in the Merkle Damgard construction. So that's like kind of like in the same way, in some sense, that block ciphers can be used to define a stream cipher, okay? So you take a small block that operates on inputs of fixed length. So the compression function will have to take a chunk of message and a previous state starting with an IV, okay? And then, so if that, for example, is of length 2n, then it spits out a tag of length n, okay? And then takes another chunk of message of length n, and then has an input then of length 2n, and then compresses to something of length n, and so on and so forth, until the very last output. So here we repeat always the same function, and the very last output is the hash. The last block, one needs to be careful to make this collision resistant and pre-image resistant. You want to make sure you pad the last block of message with some with a padding block with some information about the length of the message and those sorts of things. We're not getting into those details. I just want to mention that care has to be given to what's in the last block for this construction to be actually secure. But then, if this compression function is secure, so this is a function that operates on small blocks, if it's secure, then the whole thing is going to be secure through this construction. Okay, so the Merkle Darmgarten construction is a very classic construction method for hash functions. Now, so I just want to briefly mention here some very famous families of hash functions that are good to know. The MD family, developed by Ron Rivest, they're now considered insecure, but you'll see sometimes some of these, for example, MD5 hashes in contexts where there's no adversary. So for example, just as a checksum to verify a version of a particular document, for example, like where you know that nobody is really trying to forge anything, it would be just a sheer luck if there was a collision, because for MD5, for example, the collisions are still very, very unlikely, okay? So you'll see some MD5 hashes that are used here and there just to identify the version of a document. Then the SHA family is a family of hash functions produced by the NIST, the National Institute for Standard and Technology of the United States. So SHA-0 and SHA-1 are old versions of old instances of this family that are not considered secure. And the SHA-2 family is still currently in use and has been standardized in 2001 and has different variants, so identified by the attack size. So the attack size 224, 256, very famous one, 384, 512. And then there's two extra versions here. There's SHA-512, truncated. Okay, so you take only a block of 224 or 256 bits. Okay, and then more recently the SHA-3 family. So the SHA-2 family has the Merkle Damgard, uses the Merkle Damgard construction, while the SHA-3 family uses a newer construction called the sponge construction. So it's good to know that SHA-3 here has a different kind of design than what we have presented so far. So now let's look into what MACs are and how we can use hash functions to produce a MAC. So what is a MAC? So the goal is to authenticate data. So previously we insisted more on how to provide integrity of data with a hash function. So how to make sure that the data is what it should be. Here it's more authenticating the data, so making sure that the data comes from the right person. So in this case, Alice, for example, can assume that she has a shared key with Bob, and she sends a message to Bob. Then there is, as part of a MAC, a signature phase where a tag is produced using the message and the key. Then the message and the tag are sent to Bob, and the Bob performs a verification step. Now, one very important thing here is that this message, just as part of the MAC scheme, is not does not have any confidentiality. So the MAC in itself does not provide confidentiality. Okay, so if we want confidentiality, and authenticity, this has to be used in conjunction with an encryption scheme, and that would be called authenticated encryption. Okay, but a MAC in itself does not provide confidentiality. Bob or anybody else intercepting this particular communication could read the message. Okay, so it's really a matter of making sure this message was really sent by Alice. So what's the security of a MAC? So remember, when we talk about security of cryptographic schemes, there are some of the main items that we need to specify. First, the goal of an adversary. Okay, so the goal of an adversary here, when it comes to MACs, is to produce what's called an existential forgery. So so it's producing a valid pair message and tag such that the verification is correct using a key that was drawn at random and they don't know. Okay, so that's really the important part here, is that without the key, they're able to produce one message and one tag that yields a positive verification. Doesn't matter that it's the only message. Okay, if they can just produce one message and one tag, then the system is considered insecure because the goal of the adversary has been met. Then another item that needs to be specified as part of the definition of the security of a cryptographic scheme is the capacities of the adversary. So the rules of the particular security game that identifies the security of a MAC is the chosen message attack, the CMA. In a chosen message attack, the adversary requests from the challenger valid pairs message tag. Okay, and then they try to produce a new pair message tag that is not a part of the ones that they received from the challenger. Now, how do we create a MAC from a hash function? First, I want to talk about NMAC. Really what I want to discuss is HMAC, but NMAC is sort of pedagogically more interesting to present first, even though really it's HMAC that is used in practice. So NMAC stands for nested MAC, and the way it works is you try during the signature phase, you take your message and the key, and you hash the concatenation of that. And that alone is not secure. Instead, you need to rehash this with a different key. And the final tag is the tag that you want to use as part of the MAC. Okay, so here you have basically you separate your key into two halves. Okay, but you need therefore a sort of longer key. Okay, because you need a key here that is secure in its own right, another one that's secure. Now, how do you slightly tweak this? So first, yeah, let's mention that to verify the tag, then the person who receives the message just basically produces the tag and compares that the tag was the same as the one produced. So to verify, you just produce your own tag and check that it corresponds to the one you were sent. Now, HMAC is almost the same, except that this time we use the same key on both sides, but we XOR it with some padding, okay, that has the same length as the key. So we take bit by bit some value and we XOR it with the key. That produces technically two different inputs, okay? So you have here your message, you XOR, you concatenate it with your key XORed by some padding, and then that gives you your first hash. And then this first hash is fed into the hash function again, together with the key XORed with another padding value. Okay, so these two inputs here to the different hash function, to the different instances of the hash functions, they're different input. They're related. They both use key material. They're not technically the same, but they're just related. Okay, and that happens to be secure. But it resembles really NMAC. So if that's a little bit confusing to you, just think of HMAC as the previous one that we presented, NMAC, and that should just basically give you the high level idea of how this works. Okay, so thank you very much for your attention. And that was all for authenticity and integrity. Thank you.